how do we think of the Born approximation? Well, we can imagine a diagrammatic expression when we use propagators. Propagators are things that take a signal and propagate it in some direction. So think of your scattering center here. And of course, we were supposed to look far away, but I don't have enough room in the blackboard. I'll take this point to be far away. And now what does it say, this equation? It says that the first Born approximation, you get at R the incident wave. The incident wave has reached R. This is the incident wave at R. So I will represent this as a wave that reaches the point R. That's the first term on the right-hand side. A line reaching R, because a wave has come in that direction and reached R. On the other hand, this is a little different. What is the physical interpretation of this term? This is a wave that reached R prime. And this wave was shaken by the potential and created a source, as if the potential at R prime was a medium. The wave reached R prime, shook the potential, and then a wave appeared that was propagated by the propagator, the Green's function. It took it from R prime, it took it to R. So our interpretation of this diagrammatically is that another part of the incoming wave came here and got to the point R prime. At the point R prime, it interacted with the potential, which is a medium, and out came a wave in the direction of R. And reached there. And R prime is supposed to be integrated, but that's kind of in the figure. So this is the 0th order term. This is the 1st order term. Wave that reaches R prime, wave that reaches that thing. Now I can include the 2nd term. I could include it in this diagram, but I would confuse things. So let's draw another one. This is my thing. Doesn't look the same. I won't get it to look the same. Doesn't matter. Here is R still. And what is our 2nd wave doing? Our 2nd wave, we could put it here and imagine that you have here the e to the I k r. So here you would have e to the I k dot r double prime. So the wave reaches the point R double prime, which is here. And from the point R double prime, it interacts with the medium, that's that heavy dot, and gets propagated into R prime, which is also inside the material. So another wave, and here is R prime. And once it's propagated into R prime, it interacts with the material U, that's the heavy dot, and gets propagated into R. So that's a second order Feynman diagram. The zeroth order first Feynman diagram, the wave just reaches. First order, the wave comes, interacts once with the potential, and re-emits a wave over here. Second order comes here, interacts with the potential, emits a wave, interacts at another point, emits another wave, and gets to you. That's a pictorial description of a Born approximation, which makes it intuitive, makes it clear. It is like Feynman diagrams of field theory, in which you have some set of initial states, some set of final states, and you sort of find the ways the particles arrange themselves. So if you have an electron and a photon scattering, you have an electron here and a photon scattering, and then photon and electron out scattering. What do they do? And then in Feynman method, you think, okay, they do all what they can possibly do. They can get the photon, interacts with the electron propagates and re-emits a photon, or it may be that the photon gets emitted first, and then the incoming photon hits the other place, and it goes that way. All these things can happen, and here you have all the ways in which the waves can scatter and rescatter back to reach the observer. Basically, you're finding all possible ways the wave interact with the medium and reach you. And that's a very intuitive way. You think of it, there's a material, you're there. What do I get? Well, you get the waves that just hit you directly. And then you get the waves that hit the material and scatter to you. And then you get the waves that hit the material, scattered, hit the material again, and then got to you. And then you get the waves that did that several times. A very nice, simple picture. So that is the Born approximation. We can do one example. Let's do one example. And simplify this formula. So we did this formula, and if the potential is not spherically symmetric, you can't do more with it. But if the potential is spherically symmetric, that first Born formula, which is a very famous result, admits simplification, and you can do some of the integral. You can do the angular part of the integral because the potential is spherically symmetric, and you know how things depend on angle. So it's a nice thing to have a boxed formula that already does for you this calculation when the potential is spherically symmetric. So if V of r is equal to V of r, which is spherically symmetric, we go back to that formula, and we would have f of k of theta, we claim. We'll see if that is true, minus 1 over 4 pi. Now, this u there, remember this u was just a scaling of v in order to make the Schrödinger equation look simple. So that involves a factor of 2m over h bar squared. You still have the cube r prime, e to the minus I k dot r prime, v of r prime. So what is the intuition of such formulas? I think it's important for you, maybe you haven't seen these formulas before. If you look at a formula like this, what do you expect the answer to depend on? What is that integral going to depend on? Any opinion. Well, it certainly will depend on the potential, but now, if it's spherically symmetric, I might as well delete that. Is that right? We said it's spherically symmetric. So it will depend on the potential. That's, of course, true. But will it depend on the vector k? Yes, it better depend on the vector k, but all of the vector k or some of the vector k? It's good to think about that before doing the integral. Well, the interesting thing is when you have an integral of this form, in which this doesn't depend on the direction of r, this is r prime. But in fact, you see, there's nowhere in this formula anything to do with r and r prime. This is an integral all over space. So in fact, I can also delete now the primes. I'm integrating over all of space. There's no r on the left-hand side. There's no r left. So what for carrying primes? No need for them. Now, what I want to explain here is that this integral can only depend on the magnitude of the vector k. Cannot depend on the direction of the vector k. And because it depends on the magnitude of the vector k, it only depends on theta, which is what we wanted to say. So if before you write f of theta, you could have asked, well, how do you know this integral can depend on phi, k dependent on phi? But no, this integral doesn't depend on the direction of k. And it doesn't because you can choose your axis to do this integral whichever way you want. This is a dummy variable of integration. So if vector capital K points in this direction, you could choose the z-axis to go there, and that's it. It's only going to depend on the magnitude of that vector. So that's an important concept in here. Or you can think in another way. This answer, if I would have put another vector k prime here that is obtained by rotation, think of k prime. I put here k prime, which is obtained by a rotation acted by a rotation matrix on the vector, say from the left. Well, you would say, OK, if it's acted by a rotation, I can instead make the rotation act on the vector r. This potential doesn't change on the rotations, and this measure is invariant on the rotation. So at the end of the day, this integral does not depend on the rotation you did. So bottom line, this integral just doesn't depend on the direction of k. And we can do it by putting k, or saying k is here, and now making it explicit by putting r prime here and calling this angle theta. And we just do it. So if we call it that way, this integral is, you have minus m over 2 pi h squared. And you have the volume integral, which is 2 pi for the phi integral. So we have a theta and a phi that you integrate with respect to k. And the phi integral always gives you 2 pi, and we'll leave the theta integral here. So 2 pi, and the r integral is r squared dr. The theta integral in spherical coordinates is d cos theta. And you have here e to the minus I, length of this, length of that, cosine theta, times v of r. So things simplify even more. So the 2 pi's cancel, so you get minus m over h squared. The radial integral, it's 0 to infinity, r squared dr, v of r. And you have the angular integral. And that angular integral is easily doable. It's that and this. You can call cosine theta u and just do the integral. That integral gives you 2 sine of capital Kr over Kr. And our result therefore is, you shouldn't confuse the k with the capital K with the lowercase k, which is the magnitude of the momentum or the magnitude of the energy. So we're done, basically. And what do we have for fk of theta? We have minus 2m over k, that k, h squared, integral from 0 to infinity of r dr. 1 r got canceled. The k went out. R dr, v of r, sine of kr. So the Fourier transform got partially done. And here k, as you remember, is 2 little k sine theta over 2. So there we get the Born approximation simplified as much as we could. We couldn't do much better anymore without knowing what the potential is. But once you know the potential, it has become just a simple integral. So while the concepts that led to this result are interesting and they involve nice approximations, by the time you have this result, this is very useful. You can put an arbitrary potential v of r, calculate the integral, and out you get the scattering amplitude. So this is done, for example, for Yukawa potential, v of r is minus 1 over r. Well, we'll put a beta, just e to the minus mu r. That's called the Yukawa potential. It's the kind of modification of the electromagnetic potential in the limit in which the photon would acquire a mass. That was sort of the intuition of Yukawa. If you see, this has units of here physically mass and h bars and things like that. But if you let this thing go to 0, if mu goes to 0, you recover Coulomb potential. So that's the relevance of the Yukawa potential. Yukawa invented it while thinking of pions and thinking of the forces transmitted by pions, which are light hadrons, strongly interacting particles, but with low mass, relatively low mass compared to a proton, 1/5 of it, or even less, maybe 1/7, 1/8. And then you would have a potential of this form, and you can study scattering when you have this kind of formula. So this is solved in many books. It's also in your textbook. And in this case, f of k, the integral can be done exactly. You can plug v of r there. And the answer is that fk of theta is equal to minus 2m beta over h squared mu squared plus k squared. And k squared would be this quantity. So there's a theta dependence, and you can look at this formula, compare with the Coulomb case, take limits, plot it. It's kind of interesting. So it's easily done, and you can play with many potentials. All right, so we're done with scattering. Done like 3 lectures and a half on this subject, and I'm going to now turn into a new subject, our last subject, which is we're going to try to explain some of the basics of identical particles.